This audiobook of the original America Burning was produced by the firefighter podcast Combustible. More details on this project can be found online at www.combustiblethepodcast.com. The audio for this recording is consistent with all copyright rights and permissions associated with America Burning and is not affiliated with or endorsed in any way by the federal government or the U.S. Fire Administration. Chapter 10. Hazards Through Design. In the afternoon of August 5, 1970, fire broke out on the 33rd floor of One New York Plaza in Lower Manhattan. The air conditioning system spread smoke throughout the building. Smoke and hot gases shot upward through the gaps between floor slabs and exterior walls. An elevator was automatically summoned to the 33rd floor, the products of combustion activating the call button. The elevator jammed there, and 2 people died. Other features of high-rise design contribute to the hazards of fire. Sealed windows that cause heat to build up. Interior materials that give off thick smoke and toxic gases when afire. Utility channels and other gaps in walls and floors that spread smoke and gases. Elevators can be death traps. Exit ways can very quickly become overcrowded. When fire breaks out on upper floors, beyond the reach of ladders, firefighters must lug heavy hoses up the stairways. From the standpoint of life loss, high-rise buildings have made a very small contribution until now, but they are a matter of special concern. Recent high-rise fires in other countries with heavy life loss suggest that luck may run out for the United States. On Christmas Day, 1971, 163 died in a hotel fire in Seoul, Korea. 2 months later, 16 died and 375 were injured when fire consumed a high-rise in Sao Paulo, Brazil. As more and more Americans choose to live or work in high-rise buildings, their importance as a fire problem will increase. But high-rise buildings are not the only modern creation in which design impairs fire safety. In many homes, stairwells help to carry fire and the products of combustion upward to sleeping areas. Slim horizontal windows under the eaves of single-story dwellings, a fashionable feature of ranch-style homes, hamper rescue efforts. 2 children died in a Maine fire because firemen couldn't get through windows of this type. Tragedies of this sort have recurred many times. Clearly, fire safety lags behind other considerations such as aesthetics and economy in the design of buildings. There are a number of reasons for this. Fire safety analysis is lagging behind innovation in building design. For example, there is an understandable trend toward ever lighter structural members which reduce the cost without significantly reducing strength. Building designers introduce these innovations while 2 important questions go unanswered. First, are the structural members adequately protected from fire for the entire life of the building, as well as during a fire that may occur tomorrow? Second, are existing tests for fire safety adequate for measuring the fire protection afforded by the particular innovation? There is little incentive to invest in fire safety. Clients of building designers, to the extent that they think of fire safety at all, believe fire is a small risk in the future of their building. Or they judge that potential losses are adequately covered by their insurance policies. Owners of private homes might build in fire protection if their insurance premiums were thereby reduced, but no such incentive exists. While the reduced premium exists for builders of commercial and industrial buildings, the fire safety requirements for reduced rates often are not extensive. For the designer, the chief goals are to plan a building that serves its intended architectural function, as pleasing in appearance as can be done, and as cheaply as possible. With top priority being placed on these goals, safety becomes, for most designers, nothing more than a necessary evil for compliance with local codes. Building codes have characteristics which encourage the outlook that they are nuisances. New requirements are piled on top of old and outmoded ones, with the effect that the codes become increasingly inflexible. Often the requirements are excessive. For example, in places where the contents that will be added would all burn in about half an hour, requirements for 3 to 4 hours of fire resistance in bearing walls are not uncommon. While excessive requirements exist for some characteristics, early warning of occupants, smoke movement, and toxic gas production are virtually ignored. Tested uses and actual uses of materials can be 2 different things. The set of conditions under which materials are tested by manufacturers and private test laboratories may represent only a segment of the uses to which those materials are actually put. When a designer uses a material in a way that has not been tested, He has no way of knowing how or whether the fire safety characteristics are different. The knowledge on which fire safety standards are based is deficient. Fire safety standards are based mostly on judgments gained from actual fire experience and on a limited range of conditions used in testing. They are based, in other words, on empirical knowledge rather than fundamental understanding of the behavior of fire. This lack of theoretical and experimental underpinnings contrasts sharply with such fields as mechanical or electrical engineering. In the latter field, for example, the effects of changing the diameter of a wire, or the design of a circuit, or the amount of current pushed through the system, can be expressed as mathematical equations and predicted quite accurately. If such equations could be written to predict the effects of fire and its combustion products, then changes in a material or its use would lead to known changes in fire safety characteristics, without expensive testing. From research to application. In 1969, the Committee on Fire Research of the National Research Council published its report, A Proposed National Fire Research Program. Thorough in its scope, the report will provide a helpful guide to fire research priorities in the decade of the 70s. Much of the basic research on fire behavior recommended by the report will have a bearing on how buildings ought to be designed to minimize fire hazards. 4 years have passed since the report was issued. An assessment of what has been accomplished thus far is imperative. In areas of research where an added push is needed, additional research should be encouraged. In areas where results have begun to come in, efforts should be made to incorporate the new information into a systematic body of fire analysis and to explore the implications for codes and building design. The Commission urges the National Bureau of Standards to assess current progress in fire research and define the areas in need of additional investigation. Further, the Bureau should recommend a program for translating research results into a systematic body of engineering principles, and ultimately, into guidelines useful to code writers and building designers. No less important than the needs of designers of large structures are the needs of designers of single-family houses. The National Bureau of Standards should carry out these responsibilities in cooperation with other government agencies, nationally recognized testing and research laboratories, and with the major standards writing organizations, the National Fire Protection Association, the American National Standards Institute, and the American Society for Testing and Materials. What can be done today? The present state of fire protection engineering does not leave today's building designer in a condition of helplessness. Much of what is known about fire safety is simply being ignored. Indeed, enough is known about fire safety to permit a reliable application of a sophisticated systems approach to fire safety design. In the systems approach, in contrast to the "that's the way it's always been done" approach, objectives are set for the building as a whole, and then the most cost-effective technology is applied to meet those objectives. In such an approach, relationships among components are important, and trade-offs are sought. For example, if alarm and sprinkler systems are installed to provide quick and effective response to a fire, then fireproofing requirements for walls and floors may be reduced. Another important aspect of the systems approach is that backup measures are provided in case part of the system fails. But redundancy for the sake of redundancy is avoided. A systems approach was taken in the design of San Francisco's Transamerica building in 1971. In addition to a full sprinkler system, smoke detection devices, and a central alarm system, the designers provided the building with emergency refuge areas, two-way voice communications with public areas, and an underground communications and command control center. Windows pivot so that burning rooms can be vented. In the event of a power failure, diesel pumps will maintain water pressure, and a diesel-run generator will light exitways and power the elevators. Should city fire mains be disrupted, there is an emergency water supply. While these provisions are costly, they are offset by savings they allowed: lower fire resistance requirements for floors and corridors, the elimination of fire dampers from the air conditioning system, and a sprinkler system that permitted the use of smaller pipes. The General Services Administration has also adopted a systems approach, its first result being the Federal Office Building in Seattle. The building was given a structural integrity 3 to 4 times as strong as the most severe situation will call for it to withstand. Each story was made a self-contained, fire-resistant compartment. When a fire breaks out, and the GSA estimates that about 100 ignitions will occur in the next 50 years, one of several alarm systems will notify the Seattle Fire Department and the Emergency Control Center in the building. Immediately, a pre-recorded tape will broadcast instructions to people on the fire floor. Airflow will be adjusted to prevent smoke and other products of combustion from spreading. Elevators will be captured and reserved for handling the emergency. As with the Transamerica building, the costs of these provisions are largely offset by savings in other aspects of the building's design. The systems approach used by the architects of the Transamerica building and the GSA applies to one class of buildings. Similar approaches could be devised for other classes of buildings, including one-family residences. The Commission recommends that the National Bureau of Standards, in cooperation with the National Fire Protection Association and other appropriate organizations, support research to develop guidelines for a systems approach to fire safety in all types of buildings. A different kind of study, though a natural outgrowth of a fire safety systems analysis, is what we have designated as a fire safety effectiveness statement. This is an attempt to state in quantified terms the potential losses of life and property, both inside and surrounding the structure, should the structure catch fire. The better the design and built-in fire protection of the building, the closer these quantities will approach zero. The effectiveness statement should pay particular attention to the consequences of fires starting in areas of the structure where people or highly flammable materials are concentrated. An additional set of calculations, designed to measure the adequacy of backup measures, should be based on assumptions of system failures, such as power blackouts or non-functioning smoke detectors. While revealing whether adequate safeguards have been provided, the effectiveness statement has the added value of stating, through implication, the demands that would be put on local fire services should a fire occur. Fire safety effectiveness statements are particularly important for high-risk structures, such as shopping centers, public buildings, fuel storage depots, tankers, and chemical plants. The federal government, through the General Services Administration, has set a valuable example for the private sector through its pioneering work in fire safety systems analysis. A government-wide example should also be set in the area of fire safety effectiveness statements. Accordingly, the Commission recommends that in all construction involving federal money, awarding of those funds be contingent upon the approval of fire safety systems analysis and a fire safety effectiveness statement. The funding agency would certify that the analysis and effectiveness statement have met its fire safety standards. Product design. It is not just the large structures of the built environment that need improved design if fire losses are to be reduced. Many products need design improvement. Heating and cooking equipment, faulty wiring, and electrical appliances are major causes of fires. Together with fires caused by smoking and matches, these categories account for nearly half the fires that occur. See Table 8-2. Over the years, manufacturers and standards writing organizations have developed ever-improving safety standards in the design of consumer products. Yet some hazards have not been adequately covered. The National Commission on Product Safety in its 1970 report identified colored television sets, floor furnaces, hot water vaporizers, and unvented gas heaters as specific fire or burn hazards. Under unfinished business, possibly hazardous products the Commission did not study, were listed electric blankets, dryers, hot plates, extension cords, and space heaters. Further studies of fire experience might bring other hazards to light, particularly those that arise from wear and tear. Such studies now lie within the purview of the Consumer Product Safety Commission. The business of making consumer products safe from fire and burn hazards is, in many cases, recognizably a complicated matter. When kitchen range controls were at the front of the stove, children could reach them and cause burner accidents. Now that they are at the back, they can be hazardous to the clothing and skin of people reaching for them over hot burners. No doubt today's appliances could be made completely safe, but food wouldn't get cooked, toast wouldn't get toasted, and clothes wouldn't get ironed. But advances are possible. Within the grasp of technology are burners that can only be activated by the weight of specially designed, snugly fitting pans. Here too one must settle for imperfection. There is residual heat in the burner once the pan is removed. Further, scientists are working on the principle of generating heat within the substance to be heated, through induction of friction between molecules. Technology is also being developed to treat cigarettes and matches to minimize their potential for accidentally igniting destructive fires. Federal support may be needed to perfect these developments, and legislation may be needed to ban untreated cigarettes and matches, if manufacturers fail to adopt the improvements voluntarily. As we pointed out in Chapter 9, The Consumer Product Safety Commission is authorized by law to conduct research, studies, and investigations on the safety of consumer products and on improving the safety of such products. Since burns are a major form of injury from consumer products, it will be appropriate for that commission to devote a significant portion of its energies and resources to fire and burn hazards. This commission urges the Consumer Product Safety Commission to give high priority to matches, cigarettes, heating appliances, and other consumer products that are significant sources of burn injuries, particularly products for which industry standards fail to give adequate protection. All of the Commission's important weapons might be brought to bear against these hazards: the setting of standards of performance, design, or materials for consumer products, the requirement of adequate warning labels and user instructions, and the banning of products that are unreasonable risks to consumers. Educating the designer. Few formal education programs anywhere in the United States for architects and engineers have course requirements in fire protection engineering. Only the University of Maryland and the Illinois Institute of Technology offer 4-year Bachelor of Science degree programs in fire protection engineering. While some professional societies have committees concerned with fire safety, few designers take an interest in the committee's work. For lack of training, many designers are unable to understand highly technical reports in fire safety design. This absence of training helps to explain the unenthusiastic attention which architects and engineers, when designing buildings, give to fire safety provisions. If the situation were turned around, that is, if architects and engineers were schooled in the principles of fire safety, then undoubtedly they would participate enthusiastically in the search for alternative solutions and better codes consistent with the principles of fire safety. The Commission recommends to schools giving degrees in architecture and engineering that they include in their curricula at least one course in fire safety. Further, we urge the American Institute of Architects, professional engineering societies, and state registration boards to implement this recommendation. Registration boards could require a specific number of credit hours of fire protection engineering to qualify for state licensing for appropriate disciplines within architecture and engineering. After a suitable time to allow local initiative on this recommendation, federal funds for engineering and architectural schools might be contingent upon those schools having adequate fire protection engineering requirements as part of the degree curriculum. We recognize that, at present, if the emphasis is to be on basic principles, there is not a great deal available to be taught to architects and engineers in the realm of fire protection engineering. Deciding what can be taught and what should be taught requires careful study. The Commission urges the Society of Fire Protection Engineers to draft model courses for architects and engineers in the field of fire protection engineering. To this end, the Society should call together educators in architecture and the principal engineering disciplines to discuss what information would be desirable to teach architects and engineers. Since it will take several years to develop fire safety courses in architectural and engineering schools, then several more years before those who have had this training begin to practice, the impact of these curricular additions will not be felt for some time to come. Practicing building designers must also be educated in fire safety. The Commission recommends that the proposed National Fire Academy develop short courses to educate practicing designers in the basics of fire safety design. There is presently enough information and a wide range of technological choices, for example, total communication systems, fire retardants, fire-resistant coatings, to permit architects, engineers, and other building designers to plan buildings that are safeguarded from fire. What is needed in many cases are incentives. Positive incentives are likely to come about through example. We are encouraged that the federal office building in Seattle is serving as a beacon to the community. Now, owners of Seattle office buildings still on the drawing boards are applying the same kind of systems approach to provide the best building possible as a way of ensuring full rental. They feel they must be able to show potential renters that their building is, among other things, fire safe.